So from our work with parametrics, we know with the circle, you can get its parametric equation written like this. And if you wanted to write that in Cartesian form, you'd go through the whole process. I won't talk about it now, but you go through the process and this is what you would end up with. So it turns out that any number added on to the end here is going to just transform by translation your circle. In other words, it's slid horizontally along h units, it's slid vertically up k units. And the number in front of the cos theta or the sine theta there, you've got to keep it the same if you want a circle, and that's going to be your radius. So for these example, the centre of your circle will be hk, and your radius would be a. Now, when we come to do our work on simple harmonic motion, we're going to come up with the fact that this is your standard starting curve for displacement or location of where the particle is on a straight line. Even though we're using going around a circle as our model for what's going on, we're concerned with the projection onto a straight line, and I'm going to be concerned with the horizontal axis going along a straight line, as I've spoken about before. We could use cos or we could use sine, and there's just a phase difference there. Let's just start with cos. This is what your equation could be full of. It could be have an a in the front of it, some number in the front, which affects the amplitude, but we know that's the radius of our circle. It could have your plus c at the end here, and we know that because we're talking horizontal and because it's the x1, that's just move things along c units. So if it was -3, then it'll move it back 3 units to the left. In other words, the centre of the circle's not at the origin anymore. It's oscillating around some other point. Maybe it's oscillating around the point at x equals 8. Well, then you'd have to go +8. Inside here, we've got a couple of different things happening. This is just how fast it's going around the circle. So I'm not going to worry too much about that now, but you do appreciate that you can transform a sine or cos function by putting a number in front of the angle, and it affects the period and the frequency and so on. This here is your phase difference, and that's going to decide where on the circle we are at the start of the motion, and of course in which direction we're travelling after that. So on our line, of course, that's the projection of the particle going around the circle. This phase angle is going to tell us where we are starting. Are we starting right on our point C, that's at the centre of our oscillation? Or are we starting right out our C plus A, which is right out at the far amplitude, or somewhere in between? And if we're starting somewhere in between, which way are we going when we start? Are we heading out to the far amplitude of the motion and then coming back, or are you already heading back? So the phase is going to sort of tell you that when t equals 0, or when we chime in at whatever point, where are we on the circle, and therefore the straight line that we're worried about, and in which direction are we travelling. But that's our equation, and I want to actually do a bit of work with that equation. That's quite simple. If that's our equation for the displacement, then our velocity equation must be the derivative of that. So the derivative of a constant, gone, right? The derivative of this is a times, and this is n times minus sine times nt plus alpha. So that's what the derivative of that would be. I'm just going to go down another level now and work out what is the second derivative, or if you like, the acceleration. With respect to time, we just differentiate twice to get there. So I've got this an, that's already there. And then I'm going to multiply by. So it's going to be minus 1 times n times cos of nt plus alpha. So it's actually, what have we got? N times n and a minus 1. We've got minus n squared. We've got an a cos nt plus alpha. Now that's interesting because that's very close to the original equation. Very close. It's just missing one little bit, which is the plus c, right? So it's actually equal to minus n squared. Now instead of, this isn't just x, right? This isn't x, but I could rearrange that, and that's x minus c, right? This bit just here, this a cos nt plus alpha is equal to, if I grab that and minus it off both sides, it's equal to x minus c. So that's why I've placed that in there. So in conclusion, what I've got in the box here is very, very important because it's like how you define simple harmonic motion, how you can show or prove something's in simple harmonic motion. If you can show that the acceleration is minus n squared times x minus c, then you've shown that it's in simple harmonic motion. Now, the simple versions of simple harmonic motion won't have a plus c at the end. So this will just be minus n squared x. But it's actually x minus c to take into account it's having a center of oscillation other than the origin. Now, there's something else interesting you can do that's to do with velocity. And we've worked out here that the velocity, v, is equal to n minus na sine of nt plus alpha. That's what we've worked out that the velocity is. Now, what if I was to decide to square that? The velocity squared is equal to minus na sine of nt plus alpha squared. That's, now minus n, when you square it, you just get n squared, don't you? And a squared, and then you get sine squared of nt plus alpha. Now we know from a trigonometric identity, sine squared plus cos squared equals 1. We know that we can replace sine squared of an angle with 1 minus cos squared. So I'll do that. I've got n squared, a squared, and 1 minus cos squared of nt plus alpha. Now, how's this looking in terms of how it relates back to x? Just like before, how we managed to get the acceleration being expressed in terms of x rather than time, like here it is in terms of t, but we can express it in terms of x. Are we able to somehow make this work out that way? And the answer is yes, we can, because this is the same as n squared a squared minus, I'll just keep that n squared outside, a squared cos squared nt plus alpha. Okay, now this bit, a cos nt plus alpha is being squared, but a cos nt plus alpha is x minus c. So this is n squared, a squared minus, and this is x minus c squared. So if I can just say v squared there and put a box around this for an important point. Now this is the more difficult version. If you were at the having it oscillate about the origin, then it'd be just v squared equals n squared, a squared minus x squared. But because we've slid it somewhere, then it's v squared equals n squared, a squared minus x minus c squared, because it's oscillating around some other point other than the origin. Of course, you could just say, well, instead of x each time, I'll put x minus c. If it's moved, c units to, 3 units to the right, I'll put x minus 3 or something like that. Here's two very important equations, because those two equations are relating together the acceleration or the velocity and the displacement rather than relating it to time. But we do need to know how to relate as well to time by normal differentiation to get from one to the other there.